security basics, which is going to cover security certificates, authentication, proxies, VPNs, and API security. Not in great depth because this call is only for 1 hour, and I want to talk for a maximum of 40 minutes. And none of us are hired to be cybersecurity experts. It's not probably in your job description, but it is part of our responsibilities to protect patron information in a variety of ways, especially when we're setting up integrations between different library systems. So this is the outline and the link to view this in text format on the course website later at your leisure. And we'll start with security certificates. So first, HTTP, we talked about in the last series. So that was Hypertext Transfer Protocol, used as the foundation to create the World Wide Web of sending HTML documents between servers and clients. And it worked very well. The problem with HTTP is that communications are not encrypted. They are human readable. If somebody intercepts a message between a client and a server, they can read it for themselves. So in the early days, if you were typing a password to get into your banking system, if that was not encrypted, somebody could get that and then they would know your password. They would know your account number, whatever else was being exchanged. And that's left people vulnerable to crimes, as you can imagine. So encryption, which did exist but wasn't part of the typical protocol, uses algorithms to disguise messages as meaningless strings of characters. So instead of a password, if you have set the world's weakest password to be password 123, instead of a hacker being able to get that and see that your password is 123 and then be able to pretend to be you, it would instead look like this random string of characters until the intended recipient decodes it. So even if somebody did manage to do a man-in-the-middle attack and get your information, they couldn't do anything with it. Now, this particular string is not actually an encrypted string. It's literally a random string of characters, but it is just as meaningless as what people would see for a real encrypted message. So in the early 2010s, Google and Mozilla mandated that all major web browsers be served over HTTPS by default instead. And HTTPS uses Transport Layer Security, TLS. You might see it, or TLS 2.0, if you've seen messages about that. This protocol was previously named Secure Sockets Layer, or SSL. People still, even though SSL as a protocol was deprecated in 2011 and replaced with TLS, and the name change was because of like which company was making the protocol and they didn't want it confused. People will still say SSL a lot. They'll say SSL certificates instead of TLS certificates. But it means TLS in the modern day. And that's where the S comes from, is HTTP over SSL. We still say that. We still type that into our omnibars, even though the name of the protocol has changed. And TLS uses cryptography to make messages unreadable by humans and difficult to decode by machine. So not only can you not just look at it and know that somebody has typed password 123, it would be very difficult for somebody to even put it into a supercomputer and try to decode what that message was supposed to be. So how it accomplishes this is with initially key pairs. If you've ever seen somebody refer to key pairs, it probably means like one private key and one public key, and the two work together in asymmetric cryptography. So that means that on one side, one of the keys is used to encrypt the message, and on the other side, a completely different key is used to decode the message. So what goes into the certificate, which you can see in the browser, which anybody can receive just by visiting a website is the public key that a client is supposed to use to encrypt the message. And then when it reaches the server is the only place in the world where the private key lives, ideally. And so they are the only people who can decode the message. And then this asymmetric cryptography is a little inefficient and takes a lot of resources. So after this initial handshake, both sides agree on a different algorithm, a different key to use to both encrypt and decode the message so that the messages can go back faster and they can contain a lot more. This step, you never have to worry about it because it's completely automated. But if you're interested in learning more about the details of TLS, because I have simplified it for a bulleted list, but it is a pretty complicated process and there's lots of documentation out there and some of it is linked on the course website if you really want to know the details. So the certificate that I've been alluding to is generated by a certificate authority, or CA. And CAs are like notaries for legal documents. If you've ever had to have something notarized, like a will, you have to bring your identification with you to a notary who is approved by the state you live in. And then they will verify that you are the person you say you are by checking your identification. And any other parties present are who they say they are. And these signatures that are going on this document are real. If we didn't have a third party to generate certificates like this, anyone could just make up a signature and say, yeah, I'm totally this person and this signature is totally real. So we have certificate authorities to make sure that people aren't committing fraud. However, this is a big caveat. Notaries and certificate authorities both will only check that a person is who they say they are. They're not going to check that that person is a good person or that they have good intentions. Their job is literally just to verify that everybody is who they say they are. So if you see in your browser, and then this is a pretty wide misconception by the public that you might also encounter, that if the browser says that a site is secure, it has like a little green lock on it to prove that this is safe. It doesn't actually mean that the browser is promising that who you're connecting to is not a scammer. It's only promising that the person you're connecting to owns this domain and that all of the communications that you have with this server are going to be private. But people can still scam people in a wide variety of ways. Like you can completely replicate a known website to trick people into putting in their credentials to sign in, or trick them into giving them money. So it's not a guarantee that the website itself is safe. The process for generating these certificates, which you might have to do or might already have had to do at your library. First, a certificate signing request is generated on the server. If you're working with a vendor, you'll provide some basic information about the organization and they will generate this certificate signing request. The CSR goes to the certificate authority and the certificate authority uses it to create the certificate, and then you have to put that certificate on the server. There are two different types of certificates you might get. One can cover just one domain. For example, github.orbiscascade.org. That can be a certificate that covers just that one. Or there can be a certificate with a wildcard. So in the past, we purchased a more expensive wildcard certificate from DigiCert that was just *.orbiscascade.org. And that one certificate could be used on multiple servers to protect a variety of subdomains. That isn't as necessary today because now we have Let's Encrypt, which is a very common free certificate authority that can be installed on small servers. So that's personally what we use whenever we create a new server, is we just set it up with Let's Encrypt instead of having to pay the big organization. But every institution has their own preferences, and you probably in your role at the library, unless you're setting up servers for yourself, will be just passing certificate signing requests from a vendor over to your IT department to submit to your institution's preferred CA, and then the certificate will be installed. So that is one direction of security, is making sure that the client can be confident that they're talking to the right server. Now, the other way around, how do you know that you are talking to the correct client? How do you know that the person on the other end is really a patron of your library and not some random person who's trying to hack in and steal subscription resources? We use authentication for that. So the password-based authentication is the original one that most people are familiar with, most commonly. And it relies on the user having secret knowledge of this password. So it's literally what it says. What is the password? Like, you may pass if you give me the word that only you are supposed to know. This is vulnerable to accidental or deliberate sharing. You might accidentally share it by typing the password into a phishing website, or by using the same password for multiple systems, and then one of those systems gets compromised. People also share their passwords deliberately because they want somebody else to be able to access the account and do things in it. Or they will write it down on a Post-it note and stick it right there on their monitor. So anyone who walks into their office gets that password. So it's not the most secure way to authenticate. So usually it's combined these days with a second form of authentication, and we call that either two-factor authentication or multi-factor authentication, to require an additional proof of identity. It's not just that somebody told you the password is password 123. You also have to prove that you have permission to access this account through some other way. And some common ways are having a token, like a hardware key or an electronic fob. So those little electronic things that spit out a number, and then you have to enter the number to prove that you own this fob that is associated with the account. Or there are apps now, authentication apps, Google Authenticator. I believe Microsoft has their own authenticator. Yubico has one if you're using hardware YubiKeys. Biometrics is another way. So using fingerprints, facial recognition, or iris scanning. This would usually require somebody to have access to a smartphone in order to use these features. Sometimes it's just a digital certificate pre-installed on the device. So sometimes if there's something that you need to access through your institution, your IT department will provide you with a certificate that lives on the machine, and then that system is going to check whether that certificate exists so that only this machine is allowed in. Or there's one-time passwords that can be sent to a known email address or phone number. Now, you will likely never have to set this up directly. Most institutions will use a third-party vendor to provide multi-factor authentication, and then they will integrate that product into their preferred protocol. What you will likely have to do as a systems librarian is apply your institution's protocol to a system that you need to have patron authentication on. So Lightweight Directory Access Protocol, or LDAP, is the older version that a lot of institutions have moved away from, but it might still be applied in some institutions. So in that case, applications will check usernames and passwords directly against an enterprise directory. So wherever your student records live and whatever your IT department has set up as their LDAP protocol, that form request goes directly to the directory and it responds with the patron's information. The downside to LDAP is because it's form directory back. This has to be done for every single application that somebody signs into. So people invented single sign-on pretty early on, so that you don't have to do that. You don't have to enter your password to get into the library catalog, and then again to get into EBSCO, and again to get into ProQuest databases. So single sign-on applications will redirect users to a middleman service for authentication, and that service will use cookies to grant access across the different systems. So you only have to submit your password once. Cookies are installed on your machine and or on the server side. And then after that, every time somebody visits a new application that also has single sign-on set up, it will check for that cookie. So you don't have to just type it over and over. Central Authentication Service, or CAS, was common when I was back in graduate school in 2010-ish. That issues tickets for applications to validate, but more commonly now, especially within Orbis Cascade Alliance, is Security Assertion Markup Language, or SAML, which you might also see referred to as Shibboleth. Shibboleth is a project that implements this protocol, and that has become very common because it can be set up to bridge multiple service providers and multiple identity providers. So instead of just having one enterprise directory, you can set up, if your institution is very complex and has multiple places where identities are stored, and then service providers are on the other side, like your library catalog would be a service provider. Or if you have a different type of authentication set up for your databases, EBSCO might be your service provider. So it can accommodate and hook up to a lot of different pieces that way. One thing I want to note, and is in the course, the written course lesson for this, is you can run into issues on public computers with SAML in particular, where if somebody walks up to a computer, signs in with their own credentials, does what they want, thinks they've logged off and walks away, the next person who comes up and visits an application, because of those convenient cookies, might be automatically signed into that previous patron's account. So that is a potential security concern, and there are definitely ways around it. So if you see that happening in your institution, bring it up to your IT department. Next, we have proxies and VPNs. So most of the time, you are not setting up authentication for every single vendor. You're not going into the configuration for WorldCat Discovery Service and trying to set up SAML directly to WorldCat, or whatever other services you're subscribed to. For one thing, you would need to provide patron records for that to happen, and that's not a good idea. So instead of authenticating individual users, vendors will grant access to a range of IP addresses that are associated with your campus. So this way you don't have to share patron records or an authentication setup that gets around sharing patron records. However, it does mean that in order to access library resources off campus, patrons need a way to appear to vendors as if they're coming from on campus. Otherwise, they'll be blocked. So proxy servers were the first most common way to do that. Proxies act as intermediaries between clients and servers. So instead of a request coming directly from a patron's home computer and going straight to the vendor, and the vendor would see this IP address doesn't match anything that we have, you're not allowed to see these. It will funnel that traffic through an on-campus or a known server, and that server handles all the traffic so that it appears as if all of these requests are coming from this machine that is on campus or from a hosted machine elsewhere that you've let the vendor know about. So Easy Proxy was developed in 1999, and it rewrites URLs to funnel traffic through a library or OCLC-owned server. And it does this just by sticking this prefix on there. So myschool.edu is set up, as we talked about DNS records in the first sessions. myschool.edu will always go to this name server that is on campus. And so the traffic hits that first, and then it's not exactly mimicking, but kind of is forwarding that request over to JSTOR, for example. JSTOR is returning it back to that server, which presents it to the user. And EC Proxy used to be completely free and something that you can install on a standalone server on your campus. Now it's a hosted service most often. So the easyproxy.myschool.edu might not be going directly to your campus. You're instead providing the IP address of the OCLC servers to your vendors. A second way that people can appear to be in a location they're not is virtual private networks, or VPNs. So like proxies, VPNs process traffic from a client through a server before sending requests out to the internet. And they can mask a user's IP address. They don't always. They have to be set up to do this on purpose. That was not the original purpose of VPNs. It wasn't actually to change your IP address, although a lot of people think of it that way these days. The purpose of a VPN was to establish a secure tunnel between a client and a server that encrypts all the data back and forth. So unlike proxies, where you can simply attach that proxy prefix to any URL and it should be enough to get your students in order to use a VPN, users typically have to install software on their personal devices to connect. There are free software like OpenVPN. There's also products by Cisco that your institution might subscribe to, and then they just have to follow the instructions. So there are two types of connections to be aware of with VPNs if your institution provides one to students and faculty. Full tunnel connections route all traffic from the client through the tunnel, so you don't have to worry about it. Like literally everything somebody does on the internet is going to go through your institution's VPN server. However, if you offer a split tunnel option, split tunnel connections route some requests through the tunnel and others go directly over the internet. And this can be more efficient. So if somebody is, using their at-home computer, and sometimes they're doing Google searches, and then sometimes they're accessing the on-campus resources, you only really need the VPN for the on-campus resources. There's no reason for your school to be processing all of that traffic going through Google. So it will instead say, Google, you can go straight over there, but anything that's going to our intranet, that needs to go through the tunnel. This can cause issues if you're using both a VPN and proxy links. Like if your library has proxy links set up in your ACD list, in your Primo, and then somebody is also connected to the VPN, they might not appear to be in the correct place if their traffic is, like the proxy recognizes them as being off campus, but then by the time it reaches the vendor, it has actually just bypassed the proxy completely. So if you have that situation, there's documentation in the court's website that you can follow to resolve that. There are a couple of options. So finally, I want to talk about API security. And so in the first lesson, I used APIs that were very easy to demonstrate that you didn't need any kind of authentication to use, because that was the easiest way to demonstrate it. But in reality, when we are using APIs, it's probably got a layer of authentication over it. So the most common way that we authenticate to APIs is through keys. Providers will issue a unique identifier for a user or for an application. So for example, the Ex Libris, Alma, and Primo APIs, you will create a different key per application with different permissions on it. WorldCat, the OCLC WorldCat Discovery API, they'll just issue a key, and that represents you, the institution, and you will include this key on all of your requests. So here's an example of it adding to a query parameter. So here's an example domain that it might go to, and then you would put that as API key equals, and then you just stick it in there. Or sometimes you might, or they might require it be in a header, the header part of the request, not in the URL. And it would be like authorization bearer, and there's different types of authorizations, but I think bearer is the one that I have personally encountered when setting up services. And then the second way that APIs might authenticate people is through OAuth. So that's a protocol that is better long-term, but it's more of a pain to set up because you don't just get a static key that you can write into your code and include in everything. Instead, applications need to obtain access tokens from the server to include in requests. So I have an example for Google's, if you're using the Google Sheets or Mail or Drive APIs. When you initially set that up, you're going to have to tell the server that you're setting this up, and then it will say you need to log in to give permission on this account. So then you have to go over to a browser and enter and say it's like setting up an app on your phone and granting it permissions to get your stuff from Google. Say, yes, I grant this application the ability to see this type of information in this account, and then it will redirect back, and you can set up the server. So after setups, after that complicated process, applications may obtain refresh tokens to whenever that initial access token expires, it just pings, gets a new one until a specified period. So probably a year or more. It will just keep refreshing that authentication to work with that account until you're not allowed to anymore and you have to go in and reset it up. So here is a image showing that flow from Google. So sends a request token, you have to log in, and then it will send the authorization code, which you'll use to get the token response. And then finally, once that token is installed on the server, you can call the Google APIs. Here's a mention of cross-origin resource sharing or CORS, because you might have seen APIs specified as whether it's CORS enabled or not. So web browsers have a same origin policy that permits scripts to access resources only from the same domain and port. So if you have a web page and you have a script on it, that script can only access resources that are on your domain, whether that's on that server or a different server, but it's things that you specifically own. This only applies to JavaScript. So this may be confusing because you're like, well, I can put images over here and call them just fine. It doesn't apply to images, and it doesn't apply to server-side applications. It's a protection only to stop people from injecting JavaScript into a website that like sends resources or gets resources from a different website. CORS is actually the policy that a website owner can set to allow or restrict JavaScript access across domains. So APIs may allow broad access across all domains or to specific domains or no external domains. So you have this script over here. You can say, I want anybody to be able to call this with JavaScript from anywhere. Or you can say, nobody can use this script except people who are at my school. So an API will specify whether their methods are open through CORS or not. Now, the actual important bit, you might not want to rely on an API that does have CORS enabled because you could be exposing your information to people accidentally. So here's an example of if you were doing an asynchronous call to the analytics API from Ex Libris, and you just stuck this jQuery on a web page. There's the URL that it sends the request to. I want to get this report at this path. Here's my API key to tack on to the end of the URL as a parameter. API key equals API key, and then You'll get the data and show it on the web page, and it will be all golden. The problem with this, as you'll remember from the first lesson about JavaScript, is this script is available to everybody to see. Everybody who loads the web page will see that API key right there in plain text. It's visible on the source of the web page. It's also visible in the network tab, as we talked about the web developer tools. It'll display the request and all of the included URL parameters. So even though the Analytics API is open through CORS, you can just call it with JavaScript on any old web page. It might not be a good idea. So a more secure approach to protect your API key is to instead have a server-side application that calls whatever you need to return to the web page, and then that server-side application uses the API key. Here's another example of sending usernames as parameters. So I encountered this one in real life through the Iliad web platform API. So here's the Atlas documentation for how you call the Iliad platform API. This is the path. And then you just put in the username. So if it was JDoe, you put the username in there, and then it will return. I think this is like the top 10 transactions on this user JDoe's account. So you can go through all the steps to protect it. You make sure, like, you're putting this on a student portal, for example, just to show the Iliad requests. You ensure the portal is secure by putting SSO authentication on top of it. You ensure the key is secret, because you're not sending this over just raw in JavaScript. But if you get the logged in patron's username from this portal after they have signed in and you pass it to your script, let's say you put your script here on myschool.edu/library/iliad request.php, and then parameter user equals JDoe. Even though this wouldn't be in JavaScript, users can edit and resend requests using the network tab. So at the end of the presentation, and I didn't put this in the recording last time, but I said it was anytime you're messing with stuff in the web developer tools, you're not touching things on the server, you're only touching things on the client. And then I alluded to after the call that there is actually a way you can break things. This is how. You can use the network tab. If you have been especially adventurous, you will have found this in Firefox. There's a handy dandy edit and resend option. So here is a completely benign example from Archives West. It has sent this post query to get all finding aids for this query of Oregon Native American tribes. And this is the response that it gets, that it then gets converted and made more attractive for display on the website. Somebody can edit and resend that query. So here I have changed Oregon Native American tribes to California Native American tribes. And you can see that after hitting send and rerunning this query, the results have changed. It went out to the server and it ran this query. Different number of finding aids, different finding aids, you can see here. And you can compare these better on the course website. So you can see how this could be abused if you have something like an application on your library website that is sending a username, and then that appears in the network tab in the logs. Somebody could open this up, replace that username with somebody else's username, even though they have gone through SSO, that like they're a student, they're an active student, they have permission to see their own requests. It would be possible, theoretically, for them to get somebody else's request just by changing that username. So you never want to send any kind of private information in the URL or in a script. It's better to use some kind of database that is storing that information, and you have anonymous identifiers, preferably that change with every session. So this is just a warning to be careful. Overall, whenever you are using APIs, you don't want to accidentally open up holes for your patron security, and you want to ask questions like, what information do you absolutely need to pass to an API and it's sensitive, and then like where that should live and how it should be passed. What information is returned by the API and is it sensitive? So in some situations that might not matter if a URL returns somebody else's information because it's not sensitive. But in the case of ILL requests, you probably don't want that open. And then you have to consider where and to whom any of this information could be visible.